at convergence tests. So just a very quick reminder of the main points from the last couple of lectures. We're examining the properties of infinite series. So series is where you take a sequence of elements and you add them all together. We use this sigma notation as a summation operator. So sigma from n equals 1 to infinity of xn, that represents the infinite sum x1 plus x2 plus x3, etc. There are maybe some conceptual problems with, is that a valid thing? Because you're trying to do an infinite number of additions. How is that possible? Well, we made it rigorous by saying, well, really, we can attach a sensible value to an infinite sum if we look at the properties of the partial sums. So the partial sums, you could call them SK. These are where you just add up the first k terms in your series. There's nothing strange or wonderful about them. They're just the k numbers added together. But then you've got a sequence of partial sums. Okay, S1, S2, S3, S4. They are tracking the evolution, if you like, of the infinite series. We've got a sequence of numbers, so we studied those in chapter 1. So if that sequence of partial sums converges, which is described here, if there exists a number L, which is the limit as k goes to infinity of the sequence of partial sums, Sk, then we say that the infinite series is also convergent. Okay? We do attach this value L to the infinite series. It makes sense to attach that value to it. Okay? The partial sums, as I said, are the evolution of the infinite series. If those partial sums are getting closer and closer to some limited value L, then it makes sense to attach L to the value of the infinite series. Then we looked at a couple of important examples, and the ones we focused on initially were adding up all the powers of a half, the sum of 1 over 2 to the m, and we found that was convergent. You can explain that quite easily. It's describing the action of stepping towards 1. Doing half plus a quarter plus an eighth plus a 16, etc. You're always stepping half the remaining distance towards 1. So you're getting closer and closer to 1. The partial sums are getting closer and closer to 1. They're never going beyond 1, but they're getting arbitrarily close to 1. So they're converging. Okay, so we attach 1 as the... Sorry?
Are they closer to 1 or 0?
Closer to 1 or
0?
Well, so you have to keep this distinction. The terms are getting closer and closer to 0. The terms in the series, the bits we're adding together are closer and closer to 0. But the sum, the partial sums, when we're adding all these terms together, they're getting closer and closer. So you always have to have these two aspects of the series. What the individual terms are doing, that's when you're kind of treating it as a sequence of terms. But then what the series is doing, where you're adding them together. Yeah. So it's good to keep, you kind of have to keep your eye on the 2 things. Yeah. So that was a nice example of a convergence series. And then our second main example was the harmonic series. Very interesting series. Again, we see in this example the terms are converging to 0. So we're adding up the terms 1 over n as n gets larger and larger. So these are disappearingly small steps, vanishingly small steps. Steps are always around, but they're converging to 0. But even though that's the case, this series is a divergent series. We had an interesting proof of that, which worked by grouping the terms together and observing that we could always gather together terms of a half. If we wait around long enough, we always see a sequence of halves being generated, terms larger than a half. And there's an infinite number of those, so therefore the thing is divergent. And then last time, now we jumped around in the notes a little bit. Then at the lecture last Thursday evening, we looked at the geometric series. And we proved this theorem 2.4, which gives a complete description of geometric series. Geometric series are ones of this form here, where the terms you're adding up is a times r to the power n minus 1. So you've got some initial term a, some common ratio r. We have a complete understanding of those types of series. That's what we established last Thursday. They converge if and only if the absolute value of that common ratio r is strictly less than 1. and if we have a non-trivial series, so if the terms are non-zero, if A is non-zero, then this is going to converge if and only if the absolute value of R is strictly less than 1. And in that case, we have a nice formula for the sum of the infinite series, which is simply A over 1 minus R. So if A is non-zero and R has absolute value greater than or equal to 1, it's going to be a divergent geometric series. So our first example, where we added up all the powers of a half, that's an example of a geometric series, where A, the initial term, is a half, and R, the common ratio, is also a half. Okay. Each term is a half of the previous term. Okay. Okay, so coming back today, we're going to be looking at this section of 2.3 of convergence tests, looking at other different convergence tests. The first of these we also did last time, which is called the general term test. And we proved formally, using the definition of convergence, that if you have a convergence series, the terms must be converging to 0. If the series converges, the sequence of terms converge to 0. Or, stated the other way around, if the sequence of terms do not converge to 0, the series is a divergent. Two ways of saying the result, two ways of observing the result. So this can be used as a tool for detecting divergent series. If you examine a series and you notice that the terms are not converging to 0, then the series is divergent. So it's like a divergent test. Okay, so the next one we're going to discuss is the integral test. Now I'm only going to give, I won't give completely formal, detailed proofs of these, but I'll just get across the essential idea. And then we'll look at a collection of examples then at the end of this time. So Theorem 2.5 is the integral test. Now I know we're going to spend a lot of time talking about differentiation and integration in this unit after Christmas, but most, if not all of you, have had some exposure to differentiation and integration before, so I'm just going to make use of some of that here, because it is such a powerful idea in the analysis of series. So let's have a read of the test. Skip back to look at it on the computer for a moment. So the integral test applies in situations where the series terms, where you can recognize that the terms of the series, Am, actually come from a function, f, a function defined in the real numbers, f. And additionally, where this function is a decreasing function, and it's always positive. If you notice that you've got a decreasing positive value function f, which is supplying the values of the terms, so an is equal to this function of the indexing variable m. And what the test says, if you examine the integral of that function across all the positive real numbers, you're integrating this function from 1 to infinity. If that integral is finite, if that integral converges, it comes to a finite value, then the series where you add up the values of the ANs, that also converges. And vice versa. If the infinite integral does not converge, if the infinite integral is equal to infinity, then so is the infinite series. The infinite series is divergent also. Okay. So it's saying that there's this link between the integral and the summation. If the integral converges, the integral comes to a finite value, then so does the series. And the same holds for divergence. If the integral diverges, so does the series. Okay? So the series and the summation have the same behavior in terms of convergence. They either both converge or they both diverge. So this provides a strong link between, on the one hand, adding up all the values. This is our series, the sum of am, and in this case, the am's are supplied by this function f of m. and this object here, which is the integral of the function across all the real numbers. And we'll be examining integration in detail after Christmas. So what is this strong link? Well, the strong link becomes apparent when you draw the diagram. Now it's a decreasing function with positive values. So the function is going to kind of look like this. It's a decreasing function, getting smaller and smaller with positive values. Here's, say, 1, 2, 3, 4, 5, and so on. And we're familiar with the idea that the integral of the function corresponds to the area beneath the curve. Okay, so the integral, you see the screen? Yeah, the integral from 1 to infinity of ft dt is equal to the area beneath the curve. But you can also draw or superimpose on that picture a similar geometric object which is showing you the sum of the series. And that corresponds to not looking at the area beneath the curve, but looking at the area, the total area contained in all of these rectangles. The claim is that the sum from n equals 1 to infinity of fn equals the area of all the rectangles. Now why is that? Well, look at what area one of the rectangles has. So look at this rectangle between 2 and 3. What's the area? Well, the area of a rectangle is the width by the height. Okay, pretty simple. All of the rectangles have width 1, and they have height supplied by the function f. So the first rectangle is height f1, the second one is height f2, the second one is height f3, etc. So the area of the first rectangle is f of 1, the area of the second rectangle is f of 2, the area of the third is f of 3, and so on. So when you add up all of these quantities fm, what you're doing is you're looking at the total area in all of the rectangles, an infinite collection of rectangles. So from the diagram, it's clear that the infinite series is approximately equal to the integral. Yeah, everybody agrees with that? They look approximately the same. The area underneath the curve is approximately the area of all the rectangles. Now, what exactly is the difference? What exactly is the error in that approximation? The error is the sum of all the extra bits. So what do those extra bits look like? They're all these little bits that are poking out above the function, poking out above the curve. Okay, each rectangle, because the function is decreasing, each rectangle is poking out a little bit above the curve. Sorry, for the error. On there. The error in this approximation is all those bits. So the question is, what's the total error? What's the total measure of the error? Well, it's a neat kind of visual trick. You see, all of these errors, you can slide them all sideways. And when you slide them all sideways, because the function is decreasing, none of the errors overlap. But you can slide them all to the left. and the function is decreasing, but it's always positive. That's one of the conditions as well. So the total error is going to fit inside that first bar. Okay? We've got this infinite collection of rectangles extending all the way out to the right. For each of them, there's a little bit of an error compared with the area underneath the curve. A little bit of the rectangle poking out above the top. But you can just horizontally slide all those errors over, and you can see that they all fit inside the first rectangle. It's got area F1. For the areas, the sum of all the extra bits, and this is finite quantity. Let's call it E, which is E is certainly less than F1. Okay, so it fits inside that first rectangle, which is area F1. So we can say that the sum of our infinite series, just the area of all the rectangles, this is equal to the integral function plus E, the error. Okay. And E is definitely a finite quantity. And from this we get the link between the convergence properties of the summation and the integral. Okay? The summation is equal to the integral plus a finite quantity. So if the integral is finite, therefore the sum of the series is finite. Whereas if the integral is infinite, it's an infinite area underneath that curve. Well, you add a little extra finite bit onto that infinite area, and you've still got an infinite area. So the series is divergent. So the fact that there's this link between the summation and the integral, that proves that they're convergence properties. Now that's just a quick kind of sketch of the proof. To prove it formally and carefully, you'd have to, redo this argument correctly in terms of partial sums. Okay? But you get a similar link between the partial sum of the series, partial integral of the function. There's this error, but the error is always bounded above by F1 and so on. Okay, so that's the main idea of the proof. And the key application one application of this is deciding the convergence of any series of the form where you do sum of 1 over n to the power p, where n goes from 1 to infinity. This is the key application of this. These are called our harmonic series is an example of this, where p is equal to 1. So p is some fixed parameter here. It's the power of the n in the denominator. These are called a hyperharmonic series. Family series. Okay, so for any value of p, we've got series like this. We've already seen one of them, the harmonic series. We've seen that that's divergent. But we can settle them all. We can know the convergence property of them all now using the integral test.
Why do we say hyperharmonic?
That's just the term. It's just the name. So the harmonic series is when p equals 1. And if p equals some other value, it's just called hyperharmonic. It's just a name that's attached to it. I guess hyper suggests the action of an exponent raising something to a power, stepping up its behavior, if you will. But it's just a name. So for p equals 1, we're comparing the behavior of the series to the integral of 1 over t dt, which we all know to be the logarithm of t which converges to infinity as t goes to infinity. So the infinite integral of 1 over t dt is equal to infinity. There's an infinite area underneath the curve 1 over t. So that implies series diverges. Okay, we've already proved that by our grouping argument of halves, but we see another kind of proof of it here. And if p is not equal to 1, then we know the integral of 1 over t to the p dt, this will be t, so this is t to the minus p, so it's going to be t to the minus p plus 1 all over minus p plus 1. Okay, the presence of this factor here is not really important. We're interested in the convergence properties of that sequence of terms. And this, what does this do? This is going to converge to 0 if minus p plus 1 is less than 0, and it's going to converge to infinity if minus p plus 1 is greater than 0. So the series, the sum of 1 over n to the p will converge if minus p plus 1 is less than 0, i.e. if p is greater than 1, and diverge otherwise if p is less than or equal to 1. So, for instance, we now know about all these series, the sum of 1 over n squared, the sum of 1 over n cubed, sum of 1 over n to the power 4, all these ones converge. The integral test, it doesn't tell us straight away, it doesn't tell us what the value of the infinite series is, but it does tell us that they do converge. Oh, sorry, I'm messed up in the sorry. Yeah, I'm a bit sloppy, being a bit sloppy here. And then it's minus. Yeah, so it's this value at the top limit. Then it's minus one over. Yeah, minus p plus 1 or something. But the point is, so sorry, there's a constant term in the integral which you get from the evaluation of the indefinite integral at 1 at the beginning of the integral. But the point is the behavior of this t term there. It's going to converge to 0, disappear if minus p plus 1 is less than 0, converge to infinity.
And that's multiplying between them.
Sorry?
Between those fractions multiplication.
No, just subtraction, sorry. Because it comes from evaluating the integral at the beginning.
So that's minus 1 over.
Yeah, but that's just a constant. So this thing, so sorry, this thing will converge to, sorry, minus 1 over minus p plus 1. Sorry.
So that doesn't converge to 0 anymore.
No, it converges to that fractional quantity. It's minus 1 over minus p plus 1. Okay, sorry. I've been sloppy between the behavior of the integral and the behavior of that t term. Okay, but the main point to get is the idea of the proof contained in that diagram there. Okay, is everybody okay? Okay. So that's the integral test. So that immediately tells us about the convergence properties of a lot of series. A lot of these simple polynomial type term series. And we can make use of that in combination with we can make use of that to talk about another convergence test, which is the comparison test. So these are Theorem 2.6 and 2.7. So let's take a look at those on the notes. Okay, so the comparison tests are tests that tell you. Okay, stop talking, please. Thank you. The comparison tests allow you to determine the convergence or divergence of a series by comparing the series you're examining with one that you know the behavior of. So the integral test gave us knowledge of the behavior of a lot of simple series now. We can use that, we can build on that by comparing other series to those series. Now the comparisons happen in a couple of different ways. We'll look at the standard comparison test first. So here the series, the sum of AM is the series that we're investigating. And the series, sum of CM and sum of DM, those are two series that we know about. The C1 is a convergent series and the D1 is a divergent series. And it comes down to these inequalities here. If we can establish that our terms, the terms of the series we're investigating, if we can establish that that AM is always less than or equal to CM, then our series will also be a convergent series. On the other hand, if we can establish that our terms AM are always bigger than or equal to the terms DM, DM is a divergent series, then our series will also be divergent. There's a similar test here. The second form of it is the limit comparison test. And that's where you assess the terms of the series you're looking at, not by producing an inequality to CM or DM, but by looking at the limit of the ratio. If you take the limit of the ratio of AM divided by CM, if that sequence of ratios converges to a finite limit, that converges to a limit L, which is strictly less than infinity, then we can conclude that the series we're looking at is also convergent. See some examples of this shortly. Whereas if you look at the limit of the ratio of AM divided by DM, where DM is the term from a divergent series, if that limit comes to just be careful with the inequalities here, if that limit is a non-zero limit, so strictly bigger than 0, or not a divergent sequence of ratios at all, then the series we're looking at is also divergent. These are the comparison tests. The main idea here is if we can show that our AMs are always less than or equal to terms CM, then the term CM, the series adding up all the AMs, behaves better than the series sum of CM, because the terms are smaller. So if this converges, this one has to converge as well. Okay. Remember, a series of positive terms like this, it converges if the partial sums don't grow too big. Partial sums are a convergent sequence. But if our terms are always smaller than the terms from this convergent series, then these partial sums will always be less than these partial sums. So if these ones are converging, then the partial sums there of AM will be a bounded increasing sequences, and so they will have to converge as well. So if the sum of CM converges, then this forces the sum of AM to converge also. Whereas if the comparison goes that we show AM is bigger than another term DM for all M, then the thinking is that the sum of AM is behaving worse than in terms of convergence. It's growing faster than sum of DM. So if the sum of DM is diverging, and the terms we're looking at are bigger than those, then the sum of AM must be diverging also. So if the sum of DM diverges, so does the sum of AM. As it says in the notes there, the series that you use for the comparison will very often be one of those hyperharmonic series. And just before we look at a couple of examples, let's look at Theorem 2.9, which is the ratio test. Here we examine our infinite series by examining the limit of the ratio of one term to another one. Look at that limit as m goes to infinity. If this is convergent, if the sequence of ratios of neighboring terms, am plus 1 divided by am, if it is convergent, then the value of L tells you what the series is doing. So this will imply that the thinking here is eventually am plus 1 is going to be equal to L times am. I'll put this equals, or let's change that into an approximate. So if the limit of the ratios of neighboring terms is equal to L, that means eventually this ratio is very close to L. So eventually am plus 1 is approximately equal to L times am. Okay? Now where you've got a series where each term is some fixed multiple of the previous term, we already know about those series. Those are geometric series. I.e., the sum of am acts like a geometric series. Geometric series with common ratio L. Remember, in a geometric series, the important thing is that quantity R, where each next term in the geometric series is R times the previous one. So this ratio test says, well, eventually this ratio will be approximately equal to L, so eventually the term in our series will be L times the previous one. So this is acting like a geometric series. And the geometric series converges if L is strictly less than 1. So if L is strictly less than 1, the sum of am converges. And if L is strictly greater than 1, the sum of am diverges. If L is equal to 1, then there's no conclusion. The case L equals 1 is the borderline. between convergence and divergence for geometric series. So if we're only knowing that our sequence is acting approximately like this borderline series, we don't quite know whether it could be on the convergence side or on the divergent side. It's too close to tell. Okay, so let's see some examples of these tests in action. We can turn to the end of chapter exercises and let's look at question 8 for starters. Page 19, question 8. Look at the sum of the terms 2 over n factorial as n goes from 1 to infinity. Okay, n factorial is growing larger and larger as n grows. So the fraction 2 over n factorial, that term, the term 2 over n factorial will certainly be convergent to 0. So it passes the general term test. The terms are converging to 0, so this might be a convergent series. It doesn't guarantee that it is. Remember, the harmonic series has this property that the terms converge to 0, but it's still divergent. But at least this one has a chance of converging. And we can use the ratio test here. So we have that an, the term of the series, is 2 over n factorial. Then if you look at the limit as n goes to infinity of an plus 1 divided by an, this is the limit as n goes to infinity, so an plus 1 is 2 over n plus 1 factorial. And then we want to divide it by an, which will be an is 2 over n factorial, and we're dividing by an, so we'll multiply by 1 over an. Yeah. So this bracket simplifies a lot. You got multiplied by 2 divided by 2, so they cancel. You got n factorial divided by the factorial of n plus 1. But those are almost the same in structure. N plus 1 is the product of every number from n plus 1 down to 1, every integer. N factorial is the product of every integer from n down. So all of these factors here are contained in this factorial, so they all cancel out. And the only one that's remaining is the 1 over n plus 1. And as n grows larger and larger, it's clear how this term is behaving. 1 over n plus 1 is converging to 0. Okay. Now the ratio test says because this limit to L is strictly less than 1, we've got a limit of 0 here. The limit is strictly less than 1. So the ratio test implies that this series is convergent. Because this limit of the ratio is converging to 0, so eventually this series is behaving like a geometric series where the common ratio term r is extremely small, effectively 0. So it's going to be, that would be a convergent geometric series. So if our series is behaving approximately like that, it will also be convergent as well. Let's pick up one that demonstrates one of the comparison tests. So this might be the one in question 9. Squared plus 4. Now the hint with these ratios of polynomials, which is what this is, ratios of polynomials. So where the series term is a ratio of polynomials in the indexing variable. N is the indexing variable. So some polynomial in n divided by another one, is to compare it with the dominant power of n. And by the dominant power of n, we look what we're looking at is, well, really this numerator one is a quadratic. It's an n squared term, whereas the denominator one is an n cubed term. And as n gets large, those will be the dominant term. So it's n squared divided by n cubed. So that's 1 over n. So i.e. to do here is to compare it with the divergent series sum of 1 over n. So the dn we're going to use, the dn that we're going to use in our comparison test is 1 over n. We'll use the limit comparison test. So we'll take the limit as n goes to infinity of the term we're examining divided by an. Sorry, divided by dn. An is this term in the series. So this is the sum of an's. So this is the limit as n goes to infinity. So we're looking at 2n squared plus 4 over 3n cubed minus 2n. And we're dividing it by 1 over n. So in other words, we're multiplying it by n. So that then is the limit as n goes to infinity. So that increases the numerator to another cubic. And does that quantity come to a fixed limit? Well, yeah, it does, and you can recognize that. See, now we have to go back and think about applying our algebra of limits theorem sequences. We've got a ratio of polynomials in n as a sequence now, so if we divide above and below by the highest power of n that we see, so we're dividing above and below by n cubed, it's clear now when you look at it now that this is a convergent sequence that's converging to 2/3. Okay, because this part converges to 0, as n goes to infinity, and so does the minus 2 over n. So this limit is equal to 2/3 by the algebra of limits theorem. Sequences. So what have we done in the comparison test? We've compared our series, which is the sum of an, to this divergent series, the sum of dn. We found that the ratio of an divided by dn, its limit is 2/3. So eventually, approximately, our series is acting like 2/3 of the harmonic series. But the harmonic series is divergent, so if R1 is acting like 2/3 of it, R1 is going to be divergent as well. The harmonic series increases without any upper bound. Well, if R1 is going to be approximately 2/3 of it, then R1 is going to also increase without any upper bound.
How did you get from the second part to the last one?
This to here? So I'm looking at this and I'm dividing above and below by n cubed. Because that's the largest power of n that I see. So that will reduce it to convergent bits. Dividing above and below by n cubed. You do the same things at the top and bottom of the fractions, you're not changing it. So the limit comparison test says that the sum of an from n equals 1 to infinity also diverges. Because it compares with the harmonic series. It's approximately 2/3 of the harmonic series, and the harmonic series is diverging, so R1 must diverge also. Okay, so that's a couple of examples. One of the ratio test, one of the comparison tests. So for the tutorials this week, you can see there's a bunch of questions here which will be good to work on with your tutor, which is questions 7 through 11. Okay? Questions 7 through 11 will be good ones for the tutorial this week. And you'll see more examples there at these tests as being used. So we'll spend some more time with these convergence tests next week when I see you for the 2 sessions next week. I'll show you some more examples of them. And there's a few more topics there in the series chapter to finish off, a couple of more tests to look at, and then a series section on power series. Okay.